So hi, welcome back to the channel. And today again we are going to review a new paper. It's relatively fascinating. It's not extremely new, but again, as compared to all the legacy papers that I mentioned in the previous videos, this is quite new. This is quite groundbreaking in my opinion. And the paper that I'm talking about is this diffusion policy. Okay, this might be mirroring right now, but whatever. Fine. So I have got a lot of annotations and writings on top. So mostly I'll be reading through or I'll be referring to this document, but don't worry, I'll be sharing the screen very soon. So this paper is about diffusion policy, which is basically a visuomotor policy learning via action diffusion. This paper I'm reading is a part of my current research project that I'm doing on Stretch 3 by Hello Robot. I often mention that on my LinkedIn and everywhere. So check that out. I'll try to link a few posts in the description if I remember clearly. But yeah, so the main objective of this diffusion policy is what we are going to look into. Mainly, we'll look into what are the benefits that it is bringing onto the table with what kind of policy, how is it trying to learn policy and stuff. My main objective of going through this paper was all about understanding the code behind it, the differences that it brings as compared to the previous methods, of course, but also that how can I implement it on my own robot. So that's exactly why I went through this. So my research guide gave me this assignment last week, and this is what I've come up with. As you can see, many annotations. All my margins are just filled with small notes. But anyways, let's get into it. So this is the paper that we are referring to. I'll link this in the description of this video. What it brings is, by the way, let's start from the title itself. It says that we are going to talk about visuomotor policy learning via action diffusion. Now, what exactly is this visuomotor factor? Why visuomotor, and what were the things that were going on before this paper was introduced, and why is this special? Visuomotor basically means that the robot or the agent has gotten the ability to see as well as act in the real world. So, visuomotor, see and act in the real world theoretically at the same time. Fine. So, that's what visuomotor actually means. And the big problem that this paper, in my opinion, is trying to solve is that if there are multiple ways of doing certain task, which way should the agent take, or which way should the robot take, whatever, right? So we'll be looking into how robust this diffusion policy is as compared to others, what are the benefits that it brings, and everything around the diffusion policy. So let's get started. I will try to be as brief as possible. I want this video to be a very quick overview of diffusion policy. I'll link to many more different reviews as well from the author himself. Cheng Chi has given a talk at Lee Robot Hugging Face, probably. So I'll link that as well, which I found that he has given a lot of animations which are very helpful. So please feel free to refer that. I think another author, Russ, has also given his talk at one of these, I think it's Princeton. So his talk there was also published. I'll link that in the description as well. So feel free to look into them. My video is going to get into the technical details of these things, and I feel that Cheng Chi as well as Russ both have not really gotten into those technical intricacies, and I'm sure because like they have been busy and due to time limitations of their talks. But of course, I don't have those time limitations in this video, so I'll try to go as deep as possible, but of course their work is commendable. I just cannot keep this paper aside. I've been reading this since last week, and every night I could find something very fascinating, very new, and something revolutionary about it. Of course, I'm not trying to oversell this. There are several limitations, of course, which I won't be covering, honestly. That's not the scope. the entire scope of this video is sharing my own understanding and how I'm going to probably reproduce these results on my robot stretch 3. So fine, let's get started quickly. So again, beautiful visuals here. Uh, so what this paper is trying to present is they're presenting a robot's visuomotor policy as a conditional denoising diffusion process. So we'll look into what exactly conditional denoising diffusion process means. So don't worry about that as of now. But to give you an overview, diffusion policy learns the gradient of the policy distribution, action distribution score function that iteratively optimizes with respect to the gradient field during inference via a series of stochastic Langevin dynamics steps. Honestly, I really do not exactly understand the statistic Langevin dynamics, so I do not go into those details in this video. But I do understand some basic concepts around it, so I will try my best to explain them. But even if I don't worry about it. Uh, Without that as well, you will still get a good overview of everything. Fine. Now, the great contributions of this paper are that it is good at handling, it's actually great at handling multimodal action distributions. What is this multimodal? We'll look into that very soon. And it's exhibiting impressive training stability. We'll also talk in detail about how exactly is that happening. That we know, everyone knows that in RL, great difficulty is that we do not get good stable training. We get extremely jittery training and training curves. We do not really like them often. In fact, like in my own research, most of the time I get that zigzag, very very jittery line. I do not really often understand that if it is really learning something or just getting into a trap or something like that. So it becomes difficult for us as researchers as well to understand how well is our model performing in training. So this stability is very essential in RL, which this diffusion policy is trying to bring. We'll look into how they are bringing it, and I really like that idea, so probably I'll use that in my own research as well. Fine, okay. So next thing, so key technical contributions include the incorporation of receding horizon control. Very amazing. We'll look into that. Visual conditioning, another good concept, and the best thing that this paper is trying to bring, in my opinion, is this time series diffusion transformer. This is another kind of a transformer which takes an input as a noisy image and gives out output as a sequence of actions. We'll get into those details as well. This was a very broad, abstract idea of what we are going to talk about in this video. And of course, there are some numbers that we'll look into, very, very fascinating. But if you if you're okay that okay, yes, these are the things that you want to learn about, then you can stay in this video and read through this paper with me. But I hope by now you have got an idea that okay, this paper is for you, this video is for you. Fine, okay, so let's dive deeper into it. Policy learning from demonstrations is one of the simplest form that we have seen. People always get confused with the behavioral cloning, imitation learning. So these are very intersecting terms, and it's one of the forms where we formulate some sort of supervised regression task of learning to map observations to actions. So this is very very common. Everyone who is in RL deep learning are trying to take actions from observations, and that's what most of reinforcement learning is all about these days. So very common. But previously what we had was mixture of Gaussian, some action representations in the form of mixture of Gaussians, quantized actions. There are these papers that are cited. I have tried to refer to them, and few of them I could really nicely refer just because they were so much connected. I think Florence paper is being referred in this paper very much, like a lot for this paper, and Hu et al. 2020, this paper is also being referred. quite a lot throughout this research. So I highly recommend you to at least brief through these two papers. And another form is explicit to implicit policy representation to better capture multimodal distributions. These have been previous attempts. Now, in this particular work, what the authors are trying to do is they are trying to generate behavior via conditional denoising diffusion process on the robot's action space. This is what exactly they call a diffusion policy. If I were to formally introduce this, I would say just like instead of directly outputting an action, the policy infers the action score gradient conditioned on visual observations for k denoising iterations. I know, extremely heavy, but we'll look into these details very soon. Let's first talk about what are the key properties of diffusion policy, diffusion models that we are trying to bring in this paper. First of all, in expressing multimodal action distributions, this basically means that we are learning multiple ways of doing something, just one task. Now, you would be saying that, okay, if our data set has gotten some actions of doing the same task with multiple ways, then why would our model not learn that policy? Sometimes, as let's say, if I'm trying to make some eggs, right? So my way of making eggs would be very different from your way of making eggs. So if I'm collecting data set and you come with your idea, you also collect the data set with me on how to make eggs, then our data sets are going to be extremely non-coherent or very different from each other, right? So let's say I am the only one taking the data set, and the robot will only learn how to make eggs the way I do. It will never learn how to make eggs the way you do. Sometimes that becomes a problem. And fascinatingly, this diffusion policy tries to learn multiple ways of doing the same thing without explicitly having that well-known data set in its own domain. Fine. So that's why it is able to, so this is so diffusion policy is able to express multimodal action distributions unlike others. This provides a lot of flexibility to the model to take actions that if there are two equally likely actions possible, then which action to pick, it tries to decide on some scale. Next thing is that high dimensional output space. It means that we are trying to plan and execute sequence of actions, not just a single action. So far in reinforcement learning, what people have been doing is people have been trying to take an observation and predict the action that should be taken. It's mostly or sometimes in let's say in terms of velocity control or position control, people so far have been very much used to using velocity control. We'll see how this paper is better performing in positional control. We'll come into that. But basically, what I want to share here is that strategy, that what plan, how to plan something and how to execute that, that comes uh, very handy with this method. So infers, this property allows the policy to jointly infer a sequence of future actions instead of just one single step action, which is crucial for encouraging temporal action consistency. This is another important point that we'll be touching upon, and avoiding myopic planning. Fine. It just means that we want to avoid jokes that, okay, when if there are many actions which are not relating to each other, which are IIDs in nature, then it becomes difficult for smooth functioning. We want our robots to work, function smoothly just the way we do. Lastly, there comes the point of stable training. This is directly related to how reliable our model is, because you see, oftentimes happens, it's not very new for deep learning researchers or RL researchers to start training, and after a while, after 2 or 3 days, we come to realize that okay, whatever we were training was completely trash. We have to throw it all away. Well, This is because of probably some hyperparameter tuning or some other factor that we are not aware of. These things lead to training instability, right? Diffusion policy bypasses this requirement by learning the gradient of energy function and thereby achieves stable training while maintaining distributional expressivity. Fine. It just means that this makes our training much more reliable. So there are these three things that are happening. First, our diffusion policy is flexible. It's very strategic. Smooth and coordinated actions can take place with this. And lastly, it is very reliable in terms of training. These factors make it special. Now, how are these above properties achieved? How exactly is diffusion policy able to do it? This is what we'll be looking into. By the way, this we are still in the introduction section, and this still gives a great detailed overview of what we are going to go deeper into. So I really like the section, the way it is written. I encourage you to at least read abstract and the introduction and the key findings at the end. These three very small sections will give you a completely different perspective of how reinforcement learning is changing throughout the globe. Fine, so let's see how these above properties are achieved. First of all, they introduce closed loop action sequences. This is basically the capability to predict high dimensional action sequences with receding horizon control. Now, what exactly is this receding horizon control? What it means is we want to continuously adjust actions based on some real time observations. This continuous improvement in whatever I'm able to see right now, whatever I observe right now, I want to make some changes or take some control of this environment around me that I'm observing continuously, right? So, excuse me. Even in some cases where let's say some disturbances take place, in those cases as well, we are able to recover very well. That's why closed loop action sequences are so important. This design allows the policy to continuously replan its actions in a closed loop manner while maintaining temporal action consistency. Again, temporal action consistency is very important. We'll be talking in detail very soon. There is a small section dedicated to this particular property. Nextly, what we are able to do is visual conditioning. This is also another important factor that where we use camera input to guide robot actions. It's like giving the robot a sense of sight. And with sight, I don't just mean pixels, I mean the ability to understand the surroundings. Understanding is very important, and observations are treated as conditioning instead of part of the joint data distribution. So far, even in my own research, what I've been trying to do is I've been trying to take inputs in terms of my state space, that whatever robot actions or whatever robot state space is, I take it as an input, as well as from multiple cameras. I take all those camera images, that the continuous stream that I'm getting, as another input. So I concatenate everything and then try to train the robot in such a way that it tries to manipulate or take action in the real world. So that was my own personal way of working with images uh, with the state space of the robot itself. So robot's internal as well as external state, I would just concatenate and then feed my network, and would expect network to learn very well. Of course, this method was not very ideal, and honestly, I never thought of it. I never thought that anyone would do something different, but turns out that people are doing pretty well, and this paper proves that. So, what we are trying to do is we are trying to have this observation only for conditional purposes. We are just trying to understand that what is happening. In this formulation, the policy extracts the visual representations once, regardless of the denoising iterations. What are denoising iterations? We'll look into, but it just means that we want to extract visual representations once. This reduces the computation and enables real-time action inferences. So this is a little bit okay. It could be possible that I'm not able to explain it properly, But just consider that we are giving our robot a sense of sight, which is quite independent of its own state. So they're not concatenating, they're not doing the same mistake as I did. They are keeping visual input differently from their state space currently. Fine. So this is what I have learned, and this is what I think is important right now. Now, something that's my favorite throughout this paper is this time series diffusion transformer. What they're proposing is a new time transformer based diffusion network that minimizes over smoothing and something like that. Okay, let's cut to the chase. What they're doing is they are implementing convolutional neural networks as well as a transformer. Now, we all know that convolutional neural networks and transformers are very different. CNNs relate to images, transformers related to language, especially translation somehow. So, how are they exactly relating this? Why are they trying to relate this? What is happening here is convolutional neural networks are basically there to identify patterns in images, and transformers, on the other hand, are for understanding and generating sequences. Now, what CNNs do is they identify what is the object, where is this object exactly located. And at the same time, what transformers do is transformers plan and execute sequence of actions based on where the object is seen, right? So think of it like CNNs are saying, hey there, this is where the mug is, right? So this is where the mug is, or any object is. Now, what transformers do is, okay, let's grab and flip it or something like that. Transformers provide a sequence of actions that need to be taken from the observations that come from the camera and basically the convolutional neural network. Whatever our camera has understood about the image, about the observation, transformers taken that as an input and try to generate the sequence of actions. Now, what they have found is consistent performance boost across all benchmarks with an average improvement of 46.9%, which is huge, which is extremely huge. And this is, I think, compared to the state of the art at that time. And this is basically 2024 paper, March 2024 paper. It's hardly a year old. And that's amazing. Fine. There are a lot of different things. A few cool questions that I wanted to answer myself while reading the paper was this diffusion policy formulation. Why do we need this? Right. And Russ has given really good answers for that. He has said that diffusion policy is a high capacity plus great performance. He says that with the help of small number of demonstrations, we can achieve great results and many other points, but I'm not going to look into that. Now, let's dive deeper into DDPMs or denoising diffusion probabilistic models. Well, these are basically generative models where the output generation is modeled as a denoising process, often called stochastic Langevin dynamics. Fine. So, except for stochastic Langevin dynamics, the way I look into it is okay, here it is. This photo. This is basically a Gaussian distribution, noise distribution. And what the policy is trying to do is it is trying to generate a path or a trajectory by denoising this noise, right? This is a noise, and we are trying to, with multiple iterations, we are trying to denoise this into some proper trajectory which can be executed, and it's not just random. What this means is that our robot will move anywhere, anytime, at any point, but after some iterations it will learn to find this trajectory that's on the right 80. Fine, so that's what denoising exactly means. Okay, coming back to the paper, where we left, it was here. And this is what the denoising process equation is, and this is not exactly what they're using. They're making several modifications to it because of the kind of observations that they're getting and taking advantage of their observation type. So this is what their baseline equation is, not algorithm, but baseline equation is. And epsilon theta is the noise prediction network that we'll be looking at throughout this paper. It's, of course, this paper is all about noise prediction networks. So it you will have you will see it quite a lot. Noise prediction network with parameters theta, and basically we know this n is Gaussian noise, right? Okay, noise prediction network efficiently predicts the gradient field, fine, and there are these parameters alpha, gamma, and sigma. These are all called noise schedule, which are given in section 3.3. I think I'll be covering it, not exactly sure, but basically I think they are mostly hyperparameters which we can set, so that's fine. And also, like, one more thing about this paper is that according to them, hyperparameter tuning is not a bigger challenge. What this paper introduces is that the fact that as long as your demonstrations or your data set is correct, is good, hyperparameter tuning should not be a big problem for you. So I don't think that alpha, gamma, and sigma are big problems to choose from, but you'll get a better idea probably. I think I'll get a better idea with experimenting with actual model on my own robot. So I'll look into that soon, and probably in the next video I'll show you how exactly that's done. Fine. Now, how exactly this training taking place? So we have got a huge data set of demonstrations. We sample randomly unmodified example, that is x0, from this data set. For each example, we randomly select denoising iteration k that we have seen here, that a1k, oh sorry, atk, 83, 80. So after k iterations, we will get our desired trajectory, and there is some, and then sample a random noise epsilon k with appropriate variance for iteration k. So we know about epsilon as well, we saw that earlier. The noise prediction network is asked to predict the noise from the data sample with noise added. So this is what they're using as the loss function initially, but then they modify it to this. This is what they finally use. I think I should highlight this. This is important. Of course, like, if you want to implement this, then implementing these functions is also very important. So that's why I'm trying to highlight this. I will be implementing them later on. Anyways, let's talk about policy learning and closed loop action sequence prediction. We commit to the action sequence prediction produced by the diffusion model for a fixed duration before replanning. Okay, this is another important point that I forgot the exact number. I think they commit for 0.8 seconds, and at every 0.8 seconds, they try to replan their trajectory based on this current new observation. And this new observation can be different. So for example, if the robot is trying to move an object from one place to another, and sometimes, let's say, suddenly the uh, object gets into some sort of disturbance, and it just moves from its desired position to somewhere else, like the robot just accidentally dropped the object, right? So even if that robot has accidentally dropped the object, it will have that uh, image feedback at least. Of course, depending on the robot, there could be multiple sensors, tactile sensors, and everything. But on the most basic scenario, it will still have that camera feedback that, okay, the gripper is not holding anything. So probably whenever it will find any object in the observation space, it will try to grab that again, and then probably if it misses again, it will still try to correct itself. Of course, it's very rare to happen, but still, of course, disturbances can take place, not just due to gravity or anything, but even if a human takes away this object from the robot's gripper, the robot will still identify that, okay, where exactly is this object again. It will keep on reiterating itself, its observation, all the inputs, and try to correct it, try to make plan again and again. Replanning is going to take place again and again. So this is where closed loop action sequence prediction comes into picture. Visual observation conditioning is also important. What it means is it allows the model to predict actions conditioned on observations without the cost of inferring future states. Mm, so, okay, in diffusion, like, in diffusion, what we do is we try to have a noisy image and then try to generate less and less, least noisy image out of some Gaussian noise. What we have as an output is again some sort of an image. But in this case, we do not want an image as an output, we want a sequence of actions. And what we have is the actual image from the environment, from our own sensors, from our own cameras, right? So we want to use that. So we have modified the first equation that we saw here, and we changed this equation to accommodate our current observations along with it, our current observations, and what we are trying to find is the probability of an action given this observation. Fine. So I know it's a little confusing, but if you are into reinforcement learning and you have already read plenty of papers, and in fact, like, I think we already discussed this thing that if we are given an observation, this is how we predict an action, or this is how we find the conditional distribution, a probability, a conditional probability distribution of an action, something like that. We have already discussed that in the previous videos. You can check that out. But yeah, this is what we do in reinforcement learning, and especially in action prediction. This is what action prediction is, and after doing action prediction, we do uh, control and everything, right? So the exclusion of observation, okay, this is what it says, that exclusion of observation features from output of the denoising process significantly improves inference speed and better accommodates real-time control. It also helps. So think of it like we are not trying to predict we are not trying to predict the outcome. We are just observing whatever is around us and trying to make decision on that particular observation only. We don't care about if we pick this thing up and then place it somewhere else, what will be the new observation. We do not really care about that. Fine. So this is what it really means, that continuously we are looking at our current observation and making decisions based on that only without making any assumption, kind of a thing. It might sound confusing, but it is not. It's pretty straightforward in terms of theory. I know it's a little tricky to implement, but implementation is often difficult. I was thinking of making a video of writing the code for this as well, but turns out that it will take me some more time to understand the code. So I thought that it's been around a week or two since I published something, so why not? Fine. Okay. Let's talk about CNN-based diffusion policy. This is also an important aspect. This comes under the neural network architecture options that they are proposing. I think they are mainly dealing with two types of network architectures. First is convolutional neural networks and transformers. Second is transformers. So these two independent architectures that they might be talking about. In some cases, they are also talking about taking the output of CNNs and feeding it inside the transformer, which in my opinion is also a good idea, not a bad one. So I think that's also doable. There are some recommendations that they're giving, so we'll look into that as well. Fine. So let's talk about CNNs. CNNs are great at pattern recognition, and what do transformers do is they find the sequence of actions and they generate it. Now, transformers have this very good attention mechanism, right? I think if you have already learned about transformer mechanism, it deals with this attention mechanism, and what it what it does in the broader level sense is that it says focus on what matters, prioritize important stuff instead of analyzing everything equally, and this is how it is able to come up with great sequences in terms of, let's say, some language generation or language prediction or translation. This is because of this attention layer, and that is what the authors of diffusion policy have also tried to leverage in this work. So let's first talk about convolutional neural networks. And what we do here is we only model the conditional distribution. probability of action given observation at time step t by conditioning the action generation process on observation at time step t with film feature wise linear modulation as well as denoising iteration. Okay, fine. Secondly, what they do is they only predict the action trajectory, nothing else. Fine. In practice, they have found that the CNN based bone framework will work in most of the cases without the need of much hyperparameter tuning. So that's good. There is some disclaimer here, like, however, but for now, let's assume that CNNs work just fine. When they don't, what do they come up with? They come up with time series diffusion transformers to reduce over smoothing effect in CNN models. So what they are trying to introduce, which is quite novel, is this transformer based DDPM, which adopts the transformer architecture from Min GPT, sorry. Yeah, Min GPT. I came across this today itself, so even I am surprised that there exists something called Min GPT. But pretty fascinating that they are using a language model inside a robotic framework. Pretty interesting for action prediction. Now, neural network architecture learns from the data, right? We know that this architecture is good at understanding patterns. We know this because transformer architecture is all about understanding action sequences um, for this particular application. And what we're trying to predict is predict sequence of more and more refined actions. What we start with is basically a rough noisy guess of the actions that we might take, and what we end up with is a well defined action distribution or well defined sequence of actions. So this is our input and output structure of this transformer architecture. So let's dive into it. One of them is visual encoders. What it does is it maps the raw image sequences into latent embedding OT and is trained end to end with diffusion policy. Fine. Some things that they're using is they're using ResNet 18 without pre-training, and there are some modifications that they're making to ResNet 18. First of all, they're replacing GAP, that's global average pooling layer, with a spatial softmax pooling layer to maintain spatial information. So that's the first thing that they're changing. Secondly, what they're doing is they are replacing batch normalization layer with a group normalization layer. I think if you understand deep learning to some level, you know about what batch normalization is, what group normalization is. Group normalization is a little bit more advanced. Batch normalization has been existing since long time. Group norm is relatively new, and all those things. Fine, and why they're doing it for stable training. Now, this is important when the normalization layer is used in conjunction with exponential moving average because this is commonly used in DDPMs. Fine. So this was basic CNN architecture in ResNet 18, and there is some noise schedule that I told you that there are some hyperparameters that we can tune. What it does is it controls the extent to which diffusion policy captures high and low frequency characteristics of action signals. Simple. I don't think this needs any further explanation. There is a difference in the behavior of training and inference, and that is being talked in the section 3.4. What they're saying is that the denoising diffusion implicit models DDIM approach decouples the number of denoising iterations in training and inference. So it means that they are not similar. The number of iterations that are used in training are not exactly same as the number of iterations on inference. This allows the algorithm to use fewer iterations for inference to speed up the process. We want our inference to be very quick. Training can take time, of course, because this time our robot is not performing on the stage. But in inference, it is actually performing. It's actually doing the job that it needs to do. Right. So that's why we want our inference time to be very low and to be very quick, to be computationally efficient. And DDIM helps us decouple both the numbers. So this is how training and inference have different number of iterations, and with iterations I mean number of k, right? Okay, fine. There are a few intriguing properties of diffusion policy. I'll skim through a few of them because I've already discussed a lot of them. First one, and the most important one probably, is the model multimodal action distributions. Excuse me. So we have already discussed about what multimodal actions are, but let's look into it with an example. This is the ability to express multimodal. Okay, fine. I look at this image. By the way, I think multimodal behavior is one of the most important findings of this paper, I guess. And what they're trying to say is these are basically state of the art so far: implicit behavior cloning, BET, LSTM, GMM. Uh, Fine. So this is basically what state of the art was so far. But what diffusion policy, how is it different from everything else? So this is basically a task of push T, and our robot is basically over here, this blue dot. And what it has to do is it has to push this block that's T in shape into this green area, right? It has to some sort of merge these two, like move this robotic arm in such a way that this T also gets aligned with the green portion, the green shades. Simple. So there are multiple ways of solving this same thing. You can either go anti-clockwise or you can either go clockwise. There are only these two possible ways. Like it's in 2D, so you just cannot jump in the third dimension, right? So challenge others were facing is the fact that when you have got multiple ways of doing the same thing, sometimes the model finds a path that is sort of an average out of it. Imagine that you are driving a car and there is a tree in front of you. There are only two ways: either go from the left of it or go from the right of it. It's not like you can have any other way. You cannot just fly over a tree, right? So if a dumb policy would be controlling the car, what it would do is, okay, there's a right way, there's a left way, then of course there is a way that's right in the middle. It's just an average, right? It should work the best. Well, if you were to go with that average, you would just hit the tree very hard. You don't want to do that, and that's exactly what is happening in LSTM and BT. And you can see that in BT it is trying to it has found these multiple ways of solving this problem, but it is trying to juggle between both of them. It jumps from first policy to the other, and then the first, and then other. So that's not what is desirable. Similar things you can see in LSTM as well. In IBC, something opposite happens. Implicit behavior cloning does not really learn all the possible ways of solving a problem, right? This is because of variations probably in data set. If, as I said, that if there is only one way that I know about making X, then the robot will learn only that. It will not think. It will not understand what exactly the problem is. However, in case of diffusion policy, of course, it will only take one of these paths, but great thing about the diffusion policy is that it learns that yes, there exist two paths of solving the same problem. And of course, it can choose anything that it likes, or wherever whatever is the fastest, whatever is the most nearest way of solving this problem, the robot will try to do that. But underlying principle is that it should understand that moving from anti-clockwise or clockwise are essentially the same, and this is what multimodal behavior is. This is a very known problem in behavior cloning and imitation learning, which diffusion policy has seemed to have solved. Of course, this is whatever I've told, this is what is being written here. You can go through it once. And yeah, there is a benefit of sequence action sequence prediction instead of just one single action. So far, it was not possible for other policies just because of their framework to predict multiple actions at the same time. But in contrast, DDPM scales well with output dimensions without sacrificing the expressiveness of the model. And this is being demonstrated in many image generation applications. The main point here is that IBC, BET, and LSTM, GMM, these are all the kind of models which just predict one next action that need to be taken, and that's it. But what we have here is diffusion policy is able to generate action sequence. instead of single action. And important benefit is that we have temporal action consistency, which in simple words just means that less jerky movements. Secondly, we have robustness to idle actions, which means that we can adjust to unexpected scenarios, the example that I gave you, and we can adapt and recover to those unexpected noises. So these are different aspects that we can look into. Um, Lastly, what I'm going to talk about is training stability. How does it bring that? In IBC, there was a training instability issue. Okay, let's go to the diagram. The gray one, you see, this jittery over here. The gray one is the IBC, whereas diffusion policy is relatively smoother. In fact, like extremely smooth as compared to IBC. Right? How does it achieve that? Let's see. So, of course, IBC is basically implicit behavior cloning, and that is something similar to what we are doing in diffusion policy as well. So, what are we doing differently than IBC that makes diffusion policy so much better in terms of learning growth? What is happening here is okay, problems are that training error spikes, unstable evaluation performance throughout the training process, and this makes hyperparameter tuning very crucial. If you make small mistakes in hyperparameter tuning, probably in the beginning of the training, your training would not be useful. You will either get into some suboptimal behavior or suboptimal terrain and the loss function, somewhere not much useful. And that is another checkpoint selection difficulty. Fine. So let's look into what implicit behavior cloning was doing. An implicit policy represents the action distribution using the energy based model, EBM. Right, this is what their action prediction model was, or action distribution model was. And what they had was Z, observation, and theta is the intractable normalization constant, of course with respect to that particular action. Fine. So to train the EBM for implicit, okay. So just to summarize this thing is that let's consider this normalization constant to be some sort of a benchmark, which is of course very tricky to estimate. Now, what do we do here is we want to eliminate it somehow. The inaccuracy of negative. So there is this info NCE style loss function that is used in EBM, which you can read through it over here. It's just basically a neg log likelihood. So I think we have already learned that in deep learning. So it's not very it's not extremely new. It's not counterintuitive. We know about this. Now in practice, the inaccuracy of negative sampling is known to cause this training instability in EBMs. Well, if this z is not estimated properly, of course it will cause issues. Now what we do is we take a negative log gradient of this probability, and after doing that we just simplify the equation, and then perform the gradient, and then we compute the gradient of it. The gradient of the constant of course is 0, so this term vanishes, and what we are left with is simply approximately epsilon theta, which is basically our noise prediction network we saw earlier, right? So this is how we are trying to eliminate the calculation or computation of z, and as a result, what we have, neither the inference nor the training process of diffusion policy involves evaluating this unknown term or this normalization constant, which makes our computation easier and somehow reduces the jitteriness in the training process. I hope this makes sense, because it's just that gradient of a constant is 0. We have this normalization constant. Instead of using this equation number 6 directly, what we do, we use this equation number 8 instead, and find the probability of action. It's as simple, but it's very effective. Of course, it must have taken several months or years to discover this, and a lot of respect to the authors for that. So finally, there is one last thing, that is the connection to control theory. However, it's not really something that I am much interested in. Control theory scares me a little bit, but of course I did read through it. I was good at it when I was studying it. I did score well, but it never really interested me quite a lot. It just seemed a way to childish somehow. But anyways, I know it's very important. So what we have here is at inference time, the DDIM sampling will converge to a global minima, which actually fascinated me. This statement was quite interesting because when someone claims that they converge to a global minima, it's something that you should look into. Even I'm yet to understand. I think I'll need to get into the details of DDIM extremely at a level of coding now, of course, so that I can understand that how is it achieving global minima. It could be possible that it's a very simple mathematics round here which I'm kind of missing. Of course, I did read about it, I did understand these equations, but I'm still not able to connect it to the control theory just yet. But yes, this is a section that I'm yet to read thoroughly. Some things that we can cover is valuation matrix. There is, of course, I told you that there's an average improvement of 46.9%, and there have been different environments and different challenges that this model was tested on. I think I'm only familiar with Franka Kitchen because I have worked with this before, but it's impressive to see all these videos on the internet for diffusion policy. There are several key findings that I think I have already covered throughout the paper, so I will not be repeating in this section again. So sorry for that, but of course these are pretty standard, and you can look into that. Diffusion policy can express short horizon multimodality as well as long horizon multimodality. Short horizon and long horizon, I think we have already discussed in the previous videos, probably. If not, short horizon just means that being able to do one task that you are supposed to do. Long horizon means that uh, you are given multiple tasks and you can do multiple tasks in some particular order that suits best to you. That order's decision, the decision of like what order to follow depends on the agent itself, on the robot itself. So that's what long horizon multimodal task is, and everything else is something that we have discussed. Let me know what you think about this paper. It's really amazing. As I said, I'll be linking many different resources in the description, and I hope you go through them eventually. And I hope you enjoyed this video. All right, so that's it about this paper on diffusion policy. And let me know if you try to implement it or if you find some several good results. If you want me to implement it and show you how I'm going to do it, please let me know. I will find some way of sharing my work with you. And that's it for this one. Have a great day. Take care.